So friends, in last video we discussed about structure of simulation, or in fact modular simulation. Today what we are going to do is, this is in fact what we discussed about astrolysis, wherein there is fluid package, hypergroups and our environment. We select the compound, we select the property package, and then we get into the flow sheet, wherein flow sheet is, so this properties keeps on giving the values to the module, and modules temperature pressure requires here, so that you can calculate various properties. So this interaction keeps on going and you have got the simulation going on. So this is the typical modular mode simulation environment. And we also discussed about sequential modular approach, wherein we have got solution in sequence we get, and whenever there is a recycle, what we need to do is we need to tear the stream. That's also we discussed. You have to initialize the stream, and as you remember, stream means number of variables, like a process stream has temperature, pressure, composition and flow rate. So you have to estimate this. S1 is available to you, it generates S2, generates S3, which will in turn generates S5 dash and S4. S5 dash and S5 are being compared, and when they are same, like when I say that they are same, I mean they are accurate as far as the temperatures of both the streams are concerned, pressure are concerned, flow is concerned, and composition is concerned. So how do you do that? Like it keeps on doing it till they are converging, and what is ultimately it leads to, these are the three main things it will come. Like which stream to be tiered, as I told you in previous video, it is not necessary the recycle stream, it can be any of the stream within the loop. There are ways to determine that. Second, how do you update this? Like which method do you use to update S5 every time? You come with S5 dash, and S5 dash is different from S5. How do you update S5? Because updating means updating temperature, pressure, composition and flow. And what is the terminal criteria? What is the criteria at which you will say that now this is something where it needs to be stopped, and the flow sheet is considered to be converged. So these are the things which we are going to study. However, simulation does it on its own. The moment you specify that this is my recycle stream, this is my tier stream, simulator will do it on its own. These are various methods for updating the gas, just like we have Newton-Raphson method. Here also there are Newton method, bisection method, successive or relaxation. There are so many methods which are being used to update the streams. So with this basic, let us move to the next point, which gives us about the idea about the detailed structure of a modular mode. So this is a detailed structure of a modular mode simulator. Like it is a three-layered structure. You've got flow sheet topology, you've got unit operation module and physical property modules. And as has been discussed, every layer interacts with each other. As you can see, flow sheet topology, continuously, is interacting with unit operation modules. Unit operation module continuously interacts with physical property, and physical property again interacts with this. So what do we mean by flow sheet topology? Flow sheet topology is the sequence in which the flow is going, flow of information is going. So it basically tells us that which are the stream which are going in, which are the stream which are coming out of a process stream, and which are the stream are to be considered as an input stream to your unit operation. So say for example, you've got a pump, you've got a distillation column, you've got a heat exchanger, and flow sheet topology will tell you that which is the feed stream, which is the stream which is coming out of a pump, which is the stream which is coming out of a heat exchanger, which is the stream which is coming out of a distillation column. At the same time, which are the stream going from heat exchanger to distillation, pump to heat exchanger, likewise. So that is your flow sheet topology. It continuously interacts with unit operation modules. So unit operation modules gets input from flow sheet topology, it generates output and gives back to flow sheet topology, and that input again comes to another module. So thereby this too keeps on changing information. Unit operation modules are different modules, like you have got pump, you've got distillation column, you've got heat exchangers. Now these modules have inbuilt material balance, energy balance and other equations. But to solve all those equations, you require the values of physical properties. You might require vapor pressure, you might require a heat capacity, you might require density, you might require viscosity. All these values are available in physical property modules structure or a layer. And they require the use of temperature, pressure, which are being defined here in unit operation. So this gives information as a temperature and pressure, and this gives you the physical property, and it gives it back. So this is how these two are interacted. In the same manner, flow sheet topology pass on the information, flow of information. Some of the streams are having some temperature, pressure. So these streams needs to be interacted with physical property models, and whether they are liquid, saturated liquid, subcooled liquid, superheated vapor, and in whatever physical state they are, that needs to be determined. And how do you determine that? It is only a feed stream, but it is not going to any particular unit operation. But to determine what is the physical state of that feed stream, you require the use of physical property models. So likewise, uh, this three-layer structure keeps on interacting with each other, thereby we get the final output. We'll talk about them one by one. First is flow sheet topology. As I talked about, it gives you the sequence of the flow sheet. It will identify the recycles. It will identify the TS streams, and it naturally interacts with both unit operation modules and physical property modules. So flow sheet topology basically dictates the flow. It also tells you which is the recycle, and also tells you which is the TS stream. So basically it will give you an idea about the flow sheet. Then comes unit operation models. Unit operation models, we will also discuss this at a further length when we meet in next video. But it describes the procedure of the unit operation. It discusses about the metal balance and energy balance. It represents the library of the various equations. As I told you, other than metal balance and energy balance, there are some equation associated with the the unit itself. Like if it is a flash column, you got summation zik or 1 plus vk minus 1. If it is a distillation column, associated with distillation. Likewise, it receives input from the top level, that is flow sheet topology, and it interacts with physical property modules as well. So unit operation modules, it may be one or there may be number, but it basically takes part in solving the units. And then comes most important, physical property module. Though it is at the base, it is the topmost. Like it takes the temperature, pressure. It predicts various properties. It can be phase equilibrium, enthalpy, entropy, density, anything. And this is continuously accessed by the flow sheet and unit operation modules. So these three modules basically are shown here, isn't it? This is your flow sheet topology itself. This is your unit operation. Like this is your unit operation. This is your thermodynamic package, and it keeps on discussing and interacting with each other. So I think we'll discuss more about this too, unit operation model, physical property model, as we meet in next few videos. Thank you.